In this chapter, we will be analyzing rational expressions and equations. In this lesson, we will be simplifying rational expressions. To begin, we must first identify non-permissible values.
All right, hi everybody. So now we're going to take a look at rational expressions and equations, okay? And to start off with, as was stated before, we're going to look at simplifying these rational expressions, okay? Not equations, just an expression here. Now, let's just go right back to basics here. What is a rational function? Now, if you think back a couple years ago when we started talking about rational numbers, you know that a rational number is essentially, if I was going to kind of just cut right to the chase, it's a fraction. Well, a rational function is a fraction, okay? It's a fraction that can be written in the form of n of x divided by d of x. So, polynomial function divided by a polynomial function, with the stipulation that the denominator, that d of x, cannot be equivalent to 0. We're gonna circle back around to that. There's a reason for that, a very important reason. So n of x is going to be our numerator as a function of x. D of x is our denominator as a function of x. They're both polynomials. Now, we're going to add one extra little restriction to this. This is not absolutely necessary, but we are going to introduce it right now just so that we can kind of help students, help you guys kind of navigate the vocabulary here. We're going to insist that the degree must be higher than 1, okay? Or 1 or higher, I should say. 1 or higher, not just higher than 1, 1 or higher. So we don't want to have a degree of 0. In other words, we want no constants in the denominator. Now, that does not mean, if your denominator is a constant, that actually doesn't mean it's not not rational. It's just that in this course, in the way we're going to approach it, we are going to differentiate those two just for simplicity's sake for the time being. Okay? So for example, these are our rationals. Let's zoom in a bit here. So f of x is defined to be x plus 2 divided by x minus 1. Bear in mind, and you would have seen this a while ago, but that bar right there implies parentheses around the numerator and denominator. So polynomial divided by polynomial. Here, polynomial divided by polynomial. Now the numerator is quite simple. Okay, it's got a degree of 0, but the denominator's got a degree of 2. Okay, that's okay. Here, same thing, numerator is 1, denominator is x. Again, that's fine. Now, but let's talk about this. We're going to look at another example here, but let's talk about this one right here. Had we written this instead as r of x is equal to x over 1, okay, without this last little bit here in our definition, well, you could argue that that's rational. And actually, that's a fair argument. Yep, that would be rational. And this is exactly the same as just x by itself, right? So, is x all by itself, is that technically rational? Well, yeah, but we don't want you making that kind of a judgment call on it. It's like doing this. It's very similar to saying something like this. Let's say you've got a shape here where all sides are the same. Is that a rectangle? Yes. Yes, it's a rectangle. But to call it a rectangle is maybe a little bit confusing. It's a square. Okay, that is more precise language. Okay, to call this a rational, is this a rational? Well, yeah, but it's more precise to say that this is like just a regular old polynomial, or specifically this monomial, okay? So, same thing here. Is this rational? Well, yeah, but it probably makes more sense to think of this one as 1/5 of x plus 3. I mean, it means the exact same thing, and then this just becomes this coefficient. In which case, this is really not a rational in the same way. This is closer in structure to what we would call just a polynomial, like a linear function. Okay? So if the denominator isn't a function of x in that you don't really see the x in there, then maybe the better description of it is going to be to call it a polynomial or a radical or whatever it is that we're dealing with. Okay? So just a little bit of information about the definitions and the way we talk that through. Now let's go back to that whole issue of you can't have the denominator equal to 0. Okay? A non-permissible value, NPV, is a value for the variable that causes an expression to be undefined. In other words, it forces a division by 0 into your expression. Any number that you can put into the variable that causes the denominator to go to 0 is a non-permissible. Can't use that value here. Now please listen to what I'm saying and hear the difference. Oftentimes when I communicate it this way, what people hear is they hear me saying the variable can't be 0. No, that's not true. That's not at all what I'm saying. I'm saying the denominator can't be 0. Sometimes the variable can't be 0, but not all the time. I don't want you to assume that 0 is the non-permissible. The issue is whether or not the denominator goes to 0 for any given value that I plug into the variable. Now, if that's confusing at this point, we got to look at some examples to clarify that. Okay? So to find the NPVs, solve for x in the denominator. What basically we're going to do here is we're going to take that denominator, that d of x, we're going to set it equal to 0 and solve it. Okay? And you always got to list your NPVs before you simplify, or even as you're simplifying here. But in order to correctly state what a rational function is equal to as we simplify it, you need to include those NPVs. And I'm gonna really jump on that, I think, quite clearly. I don't think there should be any confusion about that after we're done. So really quickly, just to give a sense of what's going on here. So let's say you've got this rational expression here, x plus 3 divided by x minus 5. What we're saying here, if we want to figure out the NPVs here, is I want to know what value of x makes x minus 5 equal to 0. And the answer is I would add 5 to both sides, so look at x equals 5 here. When x is equal to 5, the numerator becomes 8, but the denominator becomes 0. I can't let that happen. Division by 0 is undefined. And so I have to state that x cannot be equal to 0. I can't allow x minus 5 to be equal to 0, which means I can't allow x to be equal to 5. That's the non-permissible. Now watch what happens. If you let x go to 0, 0 plus 3 is 3, 0 minus 5 is negative 5. If you let x go to 0, you essentially get negative 3/5. Well, there's nothing wrong with that. Negative 3/5 is fine as an answer. That's okay. So x could be 0. 0 is not necessarily a non-permissible value. Okay, you've always got to think this through as what value of the variable makes the denominator equal to 0, the whole denominator equal to 0. Okay. Anyway, let's practice some of that. Okay, so this question we're asked to determine the non-permissible values. Okay, so 3 divided by x minus 2. Well, it's the denominator that I can't allow to equal 0. So I cannot allow x minus 2 to equal 0. That's no good. So let's solve for x. And you solve for x with this kind of inequality, the same way you could as if it was an equality. You're just going to add 2 to both sides. So that means x cannot equal 2. That's my non-permissible. If you plug 2 in, it doesn't work. Over here, a little bit more complicated. Okay? Now, as we go through this, I'm just going to state this right now, but as we go through and start to work on through some of these other problems here, you're going to see that normally I would do something about this here immediately. This 3 minus x I don't like. It's not pretty to me. I would make it pretty first before I worked on this. But because the question is just asking for the non-permissibles here, what we're stating here is that x multiplied by 3 minus x, I can't allow that to go to 0. Now, this expression here has got two parts multiplied together. The x multiplied by the 3 minus x. Now, when you're multiplying two objects together, if one of them is 0, the whole answer is 0. So, either I have to state that x by itself, this x all by itself can't equal 0, or I have to state that 3 minus x can't equal 0. In either case, if I allow one of these to happen, they both can't go to 0, but if I allow one of them to go to 0, it makes the whole thing equal to 0. So either x can't equal 0, oops, sorry, I was going to write that a little differently, or negative x cannot be allowed to be equal to negative 3. If I bring the 3 over and then divide by the negatives, x cannot be allowed to be equal to 3. So if x is equal to 0 or 3, the denominator will become 0 overall. I don't even care what happens in the numerator. It makes no difference. These are my non-permissibles. Over here, I get that x squared minus 16 cannot equal 0. Now, this one is a little different, but I hope you see how it's kind of related to this one. This one was already in factored form. This one isn't. So this one needs to be factored. That denominator needs to be factored first. So I see that this is a difference of squares, so it's either x minus 4 times x plus 4 cannot equal 0. When you've got two factors multiplied together, assuming one of them goes to 0, the whole product goes to 0. So that means I can't allow either one of these factors to go to 0, which means in this case x cannot be allowed to equal 4, x cannot be allowed to equal negative 4. Those are two non-permissible values. Now in this particular case, because of the way this question is set up, because it's just the two terms there, I could also have done it like this. I could have stated that x squared minus 16 cannot equal 0. Isolating x in this case is actually a little bit easier than it is in a lot of these sorts of questions. So I could have brought that 16 over and then taken the square root, taken the square root of both sides. Now, in this scenario here, because I'm taking the square root, and what this statement right here is saying is that some number squared is equal to 16. I don't know whether they intended the positive or the negative square root of 16, so I'd have to list both of them. So it's just another way I could have answered the exact same problem. Okay, over here, 2x minus 3, this one they've almost backed off a little bit in terms of the difficulty. Again, I can't allow the denominator to go to 0. First thing I will do is bring that 3 over, so 2x can't be allowed to equal 3. And then divide both sides by 2. X cannot be allowed to equal 3 halves. That's my non-permissible. There's a few more here. All right. Here, 6x squared plus 4x is my denominator. I cannot allow that to go to 0. Actually, I just want to check one thing. No, that's it. Okay. This is not in factored form, so I'm going to put it in factored form, so I can take out a common 2x there. When there's two terms like this with x's in both of them, I'm just going to take out common factors first. So 2x, that'll leave me with 3x plus 2. Can't allow that to equal 0. Which means my factors here can't be allowed to equal 0, which means 2x cannot be 0. 3x plus 2 cannot be 0. All right, well, here, divide both sides by 2, and the reason why that's so awesome here is because 0 divided by 2 is just 0. So again, x cannot be allowed to equal 0, but I want you to bear in mind that that has not always been the case. It just, when x shows up as a factor, that is the case. Here, I would bring the 2 over, so I would get 3x cannot equal negative 2, and then divide, so x cannot equal negative 2/3. Okay? So there are my two non-permissibles. And I had a sense that I was going to get two non-permissibles because of the square there, so I knew that there was going to be two answers to that. All right, F. I notice in this case that the denominator is already in factored form, so they've already done part of the work for me. I cannot allow either one of those factors to go to 0, which means I can't allow 3x to be equal to positive 1. And then if I divide by 3, I cannot allow x to be equal to 1/3. There's a non-permissible. Here I bring the 2 over, and that negative stays with the x, so I can't allow negative x to be equal to negative 2. Then I can divide both sides by that negative, so x cannot be equal to positive 2. Now some of you are going to say, well, why didn't I do it a different way? I could have done that a little bit quicker. Yeah, I could. I just happen to know that there's going to be a lot of people here that are going to be very dogmatic about the way they approach this and be very strict in the way they approach it. And until you really get comfortable with the rules of algebra, then you kind of got to stick with it until you start to clearly see the patterns. For those of you that are comfortable with algebra, you see the patterns in the way the symbols work, you can see shortcuts to this. But if you're not, and that's fine, there's nothing wrong with that at all. Please don't hear judgment in that at all. If you're not there yet, then you simply want to take these bits at a time here. So take the term over that doesn't have an x in it. I just want you to remember that you have to leave the negative there because the negative is in front of the x. It's not in front of the 2. You only get rid of it if it's in front of the object that you're moving. Anyway, those are my 2 non-permissibles. This next one here, a little different. Okay, oops, and hold on one second. I've got to adjust my camera here a little bit. There. This question here is a little different because the denominator's actually got another variable in it. Now, there are really 3 factors, well there's 4, but there's 3 different factors here. I cannot allow 3 to be equal to 0. Well, that's okay. 3 isn't 0. In fact, that's kind of a ridiculous statement to make. However, I'm trying to make a point here. That factor can't be 0. X cannot be, 0. Y squared cannot be 0. None of those factors can be equal to 0 or else the whole denominator goes to 0. Now, this one is ridiculous. Don't even state it. You look weird when you do that. Of course, 3 isn't 0. Okay, but x could be 0, and I can't allow that to happen. So that's a legitimate restriction. Now here, to get what y is, I'd have to take the square root of both sides. Now the square root of 0 is just 0, and there is no positive or negative to 0. 0 is the exception to that rule. So in this case right here, neither x nor y can equal 0. Let's take a look at another one. Okay, x squared minus 4x minus 60. Okay, I can't allow that denominator to be equal to 0. Okay, so in order for me to really break this down nicely, I got to split that into factors. I have to factor that. Okay, now I'm just going to guess at that. So I know that each of these factors is going to start with an x, and that's why I get x squared there. Now I'm looking for factors of 60 that differ by 4. Okay, factors of 60 that differ by 4. Now don't think too hard about this, because if you struggle with this, once I show you the answer here, you're going to be like, of course, because the answer here is 6 and 10. Okay, but notice that I'm getting negative 4 here. That means between these two numbers, one of them's negative, one of them's positive, and the larger number has to be the negative one. Let's just double check that. When I multiply positive 6 by negative 10, do I get negative 60? And the answer is yeah. So that's how that factors. I cannot allow x plus 6 to equal 0, just like I can't allow x minus 10 to equal 0, which means x cannot equal negative 6, x cannot equal positive 10. Those are my restrictions. Over here, again, we've got another quadratic in the denominator. Can't allow that to go to 0, and now we're going to factor. Although on the face of it, it looks like it's a little bit more complicated with the y there, it actually doesn't change the pattern of my thinking at all. Because the product here is 2x squared, one of these has got to be 2x, the other one's got to be x. To get the 6y, these two have either got to be like 2 and 3 or 1 and 6 or some, like either the flip of that, right? So let's just take a quick look at this. If I put, now I could guess, for example, 2y and 3y, but this is a bad guess. The reason it's a bad guess, everyone here, is if I look at my original expression here, notice that there is no common factor through to everything here. There's nothing that I can factor out of all 3 terms. But if I guess a 2y right here, that would give me a common factor of 2 that I could factor out here. So that doesn't make any sense. It doesn't make sense that I could factor out a common factor of 2 here, but it wasn't common in the step before. So this doesn't even really make sense as a guess. A better guess, if I was going to do the 2 and the 3, would be to put the 2 here and the 3 here. That way I'm not introducing something common in this step when it wasn't common up here. Now let's just double check that. I know 2x times x is going to be 2x squared. Done. 3y multiplied by 2y is going to be 6y squared. Now that's negative, so one of these two is negative. To get the negative xy in there, when I multiply 2x by 2y, I'm going to get 4xy. 3y by x is going to be 3xy. Okay, So in order to get that negative there, the larger product has to be negative. So 2x times negative 2y, there's my negative 4xy. This would be positive. Okay, so that took a little bit more effort to factor, but not a ton. Here, this means that 2x plus 3y, I can't allow that to equal to 0. Now, this is an interesting question. How do I do this? Well, I guess normally what we would do in a case like this is you would isolate one of these variables. Now, it really doesn't matter which one you isolate. Don't try to do both. It's redundant. You're going to be saying the exact same thing, just in a different direction. Don't bother with that. Just pick one. Now, most of the time, in a situation like this, people solve for x. Because normally, in almost every other question that we're doing, it's x can't equal, x can't equal. So we could do that. And if we do that, we would bring over that 3y. So x cannot equal negative 3y, meaning x cannot equal negative 3 halves y. Okay? Then over here, we would do a similar sort of thing. X minus 2y can't be equal to 0, which means x cannot be equal to positive 2y. So these are my two restrictions. Now, they're interesting because they're dependent, the restriction on x is dependent on the value of y. Okay? So whatever x is, it cannot be the same as the negative 2/3 of y. Now, we could have set this up so it was y cannot equal. Doesn't matter. Okay, let's take a look at one more here. X squared plus 1, can't allow that denominator to go to 0. But you know what? That should already give you a hint as to how this is going to work here. When you square something, the result is always going to be either 0 or positive. And then what I'm doing is I'm increasing its value by 1. Okay, well, the smallest that x squared could be is 0, and then I'm adding 1 to it. There really is no way that this could be equal to 0. It just can't be. X squared could equal to 0, but x squared plus 1, at the very minimum, is going to be equal to 1. So we should get right away that there's no solution here. Or I should say, maybe not no solution, maybe that's a bad way of saying it. Well, there's no non-permissible value here. Now, if you don't like that kind of reasoning, that's okay. X squared plus 1 cannot equal to 0. That simply means x squared cannot be equal to negative 1. Now, at this point here, in order to solve that, you'd have to try to take the square root of negative 1. Then you should realize, there's no real solution here. There's no real root to that problem. So there are no non-permissible values. There's no real non-permissible values. There are imaginary ones, but again, we're not interested in looking down that path in this course.
Now we will look at the process of simplifying rational expressions.
All right, now everybody, we're going to talk about simplifying rational expressions. Now, first thing you want to do is you want to factor the numerator and denominator. It's a dead end if you don't do that. I need you to identify the non-permissible values. Very important that you do that. Now, I am going to, well, I'm going to edit what I say a little bit when we get down there. I need you to identify all the non-permissibles, okay, all of them. Now, I should say it like this. That's so that you can get the mark. It's not mathematically necessary to state them all, okay? Yeah, I wish those two aligned a little bit better. We are going to force you to name all of them so that we know you understand what it is we're asking you to do. However, as I go through this, I will repeatedly mention that at times we're going to state non-permissibles when it's not absolutely necessary to do so. Okay, so I can differentiate when it is necessary to do so. Then we're going to simplify if possible, and really what this means is this means finding the ones. Okay, so for example, well, here, let me show you here. If I've got an expression that's, let's say, x times x plus 3 divided by x plus 3, the x plus 3 divided by x plus 3 is going to be equal to a 1. Okay? So then this becomes, now, and the reason I can do that sort of division here is because between the x and the x plus 3, there's multiplication, and then separating the numerator from the denominator is division. there is some freedom here. I can do multiplication and division. I can play with the order a little bit here. So I can divide those first to get 1 and then multiply by x, and so the answer is x. That's true. Excuse me, that's true so long as I never let x equal -3. Because if x is equal to -3, that's a non-permissible value. Now in this case, I would absolutely need to state that, because when you look at x all by itself, I can't tell that there's a problem with any value for x. But this is where I got that result from, and in this expression here, x cannot equal -3. So because that's not visible anymore, I need to state it in order for this to be equal to the original. Now, what are some common mistakes that people make? Well, they'll do this. X plus 3 divided by 3, they'll cancel the 3's out. You can't do that. You cannot do that. You can only divide out factors. Well, 3 here isn't a factor. Okay, it's not a factor. Factor means two things multiplied together. Here, x and the 3 are being added. This is an addend. Now, what I could have done is x plus 3 divided by 3. I can distribute that 3. This is exactly the same as 1/3 of x plus 3. It's exactly the same. And so then I could distribute that and make that x over 3 plus 3 over 3, and then 3 over 3 is equal to 1. So I could have written this, okay, I could have canceled those 3's and written that as x plus 3 plus 1. See, the problem is most people, when they do this, they'd forget to distribute the 3 to the x. They think it only cancels there, done. And that's not true. That 3 has to be distributed to both of those. The same thing is happening here in this term. What I could have done was made this x over x plus 5 over x. And so this is 1 plus 5 over x. I could have done that, but you can't just cancel the x's out. And then again, the same thing here. Now this is even more complicated. Whoops, sorry, this one's even more complicated because there's binomials in the numerator and denominator. So you really can't just cancel those pieces out here. Okay? That bar, again, implies a set of parentheses, and you have to do what's inside the parentheses first. You have to deal with that first. And then you can cancel factors. And because x is not a factor in this question, okay? X by itself is not a factor in this question. I can't cancel that value of x. Now, other things to look out for. If you ever had like an x minus 3 over a 3 minus x in a problem, okay, those look similar, but they're not. And when you take a good look at this, you should notice that the denominator is a little on the ugly side. There's just something that's not quite right about it. It's in the wrong order. It's totally in the wrong order. So remember, I'm going to put these things in the correct order. I'm going to treat this as if it was 3 plus negative x. And so that when I change the order, I get negative x plus 3. Now I like that. It's in the correct order now. But now I got a negative in front here, and I don't really like the negative in front there. So I am going to factor out the negative, and that's going to give me negative x minus 3. Now the numerator and the denominator are the same. I can cancel those out, and that will be equal to, now bear in mind, it's a negative on the denominator here. So this is 1 with the negative down there. That negative down there makes the whole thing negative. If you've got a negative in the numerator or a negative in the denominator, the whole thing is negative. So this is equal to negative 1, so long as x is not allowed to be equal to 3. So if x is equal to 3, then it actually becomes undefined. Now, you could either factor it like this or get used to the fact that x minus 3 divided by 3 minus x is just going to be negative 1. You can just recognize that that sort of pattern will always hold and just jump to the answer. That's preferable, but not necessary. You feel totally free. If you ever get in a corner here where you're looking at a problem and you're not sure what to do, if you ever see something that doesn't look very pretty, like you look at it and instinctively you think, that looks backwards to me, put it in the right order. And that should usually clarify any kind of misunderstanding. Here, bear in mind that x plus 4 divided by 4 plus x. Remember that order does not matter with addition. Okay, it's commutative. And so I could very easily change that to x plus 4 over x plus 4. And again, in which case the answer is 1, so long as x does not equal negative 4. Because if x equal negative 4, then it's undefined. So you would need to state that really to make a true statement about how it simplifies. Okay, so for the next few questions here, we're going to simplify and list the NPVs. Now, you really shouldn't have to, as a teacher, I really shouldn't have to include this and list the NPVs. When I say simplify, it should be implied that you need to express the NPVs. That's the only way that you can actually make that correct here. Now, first thing I'm going to do is we're going to factor. The numerator is a difference of squares. The denominator, there's not much going on in the denominator other than the fact that there's a common factor of 3. Okay, now, I see a factor of x minus 5, a factor of x minus 5. So I can divide those out. X minus 5 divided by x minus 5 is just going to be 1. So this is going to be x plus 5 divided by 3. However, these, if I just leave it like that, these two are not exactly the same. They're equivalent to each other. These are not exact. This is not equal to this. They're equivalent, meaning that they overlap for almost every value of x, but there's a little bit that they don't overlap on. And where don't they overlap? Well, I could let x equal 5 here. 5 plus 5 is 10 divided by 3, 10/3, and that's fine. But if you let x equal 5 here, this one becomes undefined. Okay, so this one's undefined at 5, this one has no problem there. So to make them equal, I have to state, x cannot equal 5. And now this expression is actually equal to the one above it. I need to state that because that restriction is visible here and now it's gone. In fact, if you really want to be technical about this, we call this a removable discontinuity. Okay, it's a gap in the value of x, but notice that I was able to get rid of it by factoring and canceling. So I was able to remove this little discontinuity, this little hole in it. In the graph here, let's take a look at this one. 2 pi r squared plus pi over pi d. Okay, well, what's common in the numerator is obviously that pi. So 2r squared plus 1 over pi d. And now I'm going to cancel out the pi's there. Pi divided by pi is 1. Now we could, because pi is a symbol, you could force this expression to be such that you treat pi as a variable, but that's an awkward way to do it. That's not a very natural way to interpret that symbol. For almost everybody on the planet, that symbol right there refers to a very specific number. That can't be anything other than 3.14159 blah 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 and so on and so forth. So when I cancel that, pi divided by pi is 1. There's no non-permissible, like I can't, it would be goofy to say that pi cannot equal 0 because pi doesn't equal 0. Okay? Now, I could state at this point here that d cannot be equal to 0. That's a non-permissible, but it's not necessary to state it because I can already see right now that d is in the denominator. I know that d can't be equal to 0. So it's not necessary to state this. However, in this particular course, you should state all of the non-permissibles. In the previous question, it was necessary to state that x can't equal 5 because it was no longer a problem in the denominator. Here, it still is. And I can clearly see that in my expression here. However, to get the mark, to jump through that hoop, you need to state that d cannot equal 0. Over here. 25r squared plus 10 over 25r squared. Okay, well, I got to factor first. There's a common 5 in the numerator, which will get me 5r squared plus 2 divided by 25r squared. Between the 5 and the 25, there's a common factor. Though there's no common factor between 5r squared plus 2 because I got to treat that all as one factor. I can't just grab a piece from it and cancel it with a 25. I have to use an entire factor here. Well, 5 is sitting on its own as an entire factor. So if I cancel that out with the 25, okay, I'm going to be left with 5r squared plus 2 in the numerator over 5r squared. And that really is as far as I can go. I cannot cancel that 5r squared divided by that 5r squared. Okay? Because in the numerator, remember, there's a set of parentheses around the whole thing. I would need to add those two together first before I move on and do the division. If I cancel right away like that, I'm doing the division too soon. I can't do that. So that is as good as it's going to get. Okay? With the stipulation that r cannot be equal to 0, because that would force the denominator to go to 0. Again, this is not necessary to state mathematically, but again, to get the mark, you need to state the non-permissibles. All right, let's keep going here. 18, what do we got here? 18x cubed minus 30x squared. Okay, so there is a common factor of, let's say, 6x squared there, which will leave me with 3x minus 5 out of the numerator. The denominator is 24x squared. Now, between the 6 and the 24, the 6 is a common factor, so that will cancel, give me a 4 down here. Then the x squared is actually completely cancel. X squared divided by x squared is going to be 1. So we're left with 3x minus 5 over 4. Now, because I canceled the x squareds out, and like they're gone, I now have to be very clear as to what restriction just disappeared. Okay? The restriction was that x could not equal 0. If I don't say that, then these two are not actually equal. Because this one here did have a restriction at 0, and this one here, the way it's written, doesn't. So what I have to do is I actually have to state the restriction to make sure that now this line of my work here has the restriction x cannot equal 0. Here it was obvious, here it's not obvious, so I have to make it obvious. Okay? This one. Okay, well the numerator is a difference of squares, so x minus 3, x plus 3. Then the denominator is a quadratic. The factors of 6 are going to be 3 and 2, so let's see. Because the middle term here is negative, I need the larger of those to be negative, so it's going to be negative 3x plus 2. And now the x plus 3's are going to cancel, and they're going to become 1. X plus minus 3 divided by x minus 3 is 1. Multiplied by what's left over isn't going to change it, but I have to state, I can't cancel the x minus 3's without stating, hey, x cannot be allowed to be equal to 3. Because that line has that restriction, this line doesn't until I state it. Now, this is going to do a good job of illustrating what I meant before here. Now, that is mathematically what is necessary. There is another restriction here, x cannot equal negative 2, but I don't need to necessarily write it because I can see it right there. I can't allow the denominator to go to negative 2. However, to get the mark in this course, you need to state that non-permissible because we need to know that you recognize that it's there. So you need to state them all, not just the ones that we've canceled, but the ones that survive to the end here. Okay? Now, I gave you a little bit of vocabulary a few minutes ago. I'm going to give you a little bit more here. Because this was the one that got canceled, again, I call this a removable discontinuity. Discontinuity meaning just a gap in the graph, gap in the value of x. This one here, because it's a restriction that survives to the very end and it lives on in that problem, we call this an essential discontinuity. I can't get rid of it. Discontinuity. Okay? So removable versus essential. Let's keep going. Okay, difference of squares in the numerator, x minus 5, x plus 5. And then here, 2x. And then factors of 5 that are going to add up to 9 when I use that 2 there. Well, 5 is either going to be 1 and 5 or 5 and 1. But that 9 there really indicates that I got to get close to that 9. So I'm going to put the 5 here. So 2 times 5 is going to give me 10. And I'm going to want that to be the larger because it's negative. So I'm going to want the larger product here to be the negative one, the smaller one to be the positive one. So 2x times negative 5 is negative 10x plus 1x. There's my negative 9. So x minus 5 cancels with x minus 5. So this is going to reduce down to x plus 5 over 2x plus 1. The removable discontinuity, the one that I got rid of, was that x cannot equal 5. The essential one that stayed on till the very end, if you bring the 1 over, divide by 2, will be negative 1/2. Okay, removable, essential. All right, here. Okay, now my numerator is a difference of squares. So it'll be 5x minus 1, 5x plus 1, not a problem. Before I even get into factoring this, my denominator does not look right. It does not look pretty. They're in the wrong order. So I'm going to move that negative 10x up to the front first. So 5x minus 1, 5x plus 1. And now I'm going to take out what's common here. And what looks like it's common here is going to be a 2. Now, because I don't necessarily like the negative in front of the x, I'm going to take out a negative 2, which will make this 5x minus 1. And so now 5x, and bear in mind, all I've done, what has motivated that little bit of work in the denominator is the desire to make it look pretty, to make it, to set it up in standard form where I've got the x in the denominator and it's the highest power first going down to the smallest power. So now 5x minus 1 cancels 5x minus 1. I'm going to be left with 5x plus 1 over 2. And I'm just going to move that negative so it's in front of the whole thing. That doesn't really matter, but as long as it's clearly separated there. The removable discontinuity, okay, so it's a binomial here, so I can't let 5x minus 1 go to 0, so bring the 1 over, divide by 5. It's going to be positive 1/5. Now, I might also state that I can't allow 2 to be equal to 0, but that's not necessary. 2 isn't 0. Don't state it. All right, okay, well now this one's looking a little messy. In the numerator here, I'm going to take out what's common, and that's going to be a 7x squared, and I'm going to be left with x squared minus 5. In my denominator, first of all, I'm going to change the order in my denominator. I don't like the order in which it's written because I want the higher power up front. Okay, so I'm going to stick with that. That looks prettier to me. Okay, and now what I will do is take out what's common. What have I got there? I've got a 7x squared. And I'm going to be left with 3x squared plus 2. Okay. Now, the 7x squared over the 7x squared, those are going to cancel and give me a 1. So I'm going to be left with x squared minus 5 over 3x squared plus 2. Now, the removable discontinuity, well, the one that I just canceled out there, was that x cannot be equal to 0. Okay? So, all by itself, x can't be equal to 0. The other discontinuity I have, the essential one, is that, well, now I got to take a look at this. That's a little bit more complicated. So let's just go over to the side here. 3x plus 2, I can't let that go to 0, which means I can't let 3x squared be equal to negative 2. I can't let x squared equal negative 2/3. And as soon as I get to this point here, it becomes really clear to me. The next thing I would do is take the square root. But what's on the other side there is negative. So, you know what? That's not even going to cause me a problem. My x squared, at this point, because I'm working with just real numbers, I'm not going to get a negative anyway. So that was it. That was as far as I needed to go. My restriction here is x cannot equal 0. That was that removable discontinuity. There are no essential discontinuities. All right, this next one. Okay, a little bit more complicated because there's a bunch going on here. I've got two difference of squares here. So it's going to be x minus 7, x plus 7. X minus 4, oh, I'm running out of room, x plus 4. Yikes. All over. Well, in this case here, the first terms are going to be x. And then factors of 28 that get me negative 3 there, well, that's going to be negative 7, x plus 4. Ooh. x minus 7 will divide to get 1. X plus 4 will divide to get me 1. So this is going to be left with x plus 7 multiplied by x minus 4. Now I have got 2 removable discontinuities here because I canceled the 2 of them. The denominator is completely gone. X cannot equal 7. X cannot equal negative 4. Those are my removable discontinuities. Now, you might want to expand that out. That is something you're going to have to kind of figure out with your teacher, whether that's something that your teacher wants you to do here. This is going to be plus 3x minus 28. I still have to state the non-permissibles every step along the way. Once I've eliminated the terms, I need to continue to state this or else it's not true. But whether you have to expand that one out at the end, that's kind of up to your teacher. Okay, let's keep going. X plus 2 squared minus x plus 3 squared. Okay, well, okay, that numerator, that's a difference of squares. It's a little complicated, but it's a difference of squares. That is going to be x plus 2 minus x plus 3, x plus 2 plus x plus 3. Now, you've looked at questions like this before in this course. It's just been a while. Okay, where the factoring has these extra little terms in there. Don't let that throw you off. If you have to go back and review. The denominator here would be 2x, x. I'm looking for factors of 5. Now, in the previous question I had like this, I put a 1 here and a 5 here. It's because the middle term was 9. In this case, it's 3. I think I'm going to put a 5 here and the 1 here. Now, does that work? Yeah, as long as I make this a positive 5 and a negative 1 there, because then this becomes negative 2x plus 5x, and there's where I'm getting 3x from. All I'm really doing here is just guessing and checking. That's it. I'm not doing anything. If it looks like I'm super clever, please, I'm not. I really am just guessing and checking to see if my guesses work. That's usually a pretty good way to factor at this level. Here, if I drop the parentheses inside here, the negative is going to distribute through. This will be x plus 2 minus x minus 3. This will become x plus 2 plus x plus 3 all over 2x plus 5 x minus 1. And now, x minus, oh, that's interesting. The x's are going to disappear. That's not going to lead to a non-permissible because I got rid of those by adding them. That's fine. 2 minus 3 is going to be negative 1. And then here, this will be 2x plus 5 all over 2x plus 5 x minus 1. Okay, good. Now I'm at something that I can play with here. I can cancel the 2x plus 5s. I'm left with a negative 1 over x minus 1. Now, x cannot equal. The removable discontinuity is going to be negative 5 over 2. Bring the 5 over from the equal sign, divide by 2. The essential discontinuity will be positive 1. That's what makes the denominator equal to 0, and I can still see that at the very end. That's why it's essential. Okay, here, last question we're going to look at here. Notice that what they've done here is we've got this x plus 2 squared minus x plus 2 minus 12. This is in the form of a quadratic. I don't know what x is. So as a result, I don't know what x plus 2 is. I mean, you might as well call it a. I mean, I don't know what x is. I have no idea what x plus 2 is. That whole thing is just as unknown as x. So let's just treat this as a squared minus a minus 12 over x plus 5. Just to start off with. This is a very common tool used by mathematicians. Now, let's factor the numerator. Now, a squared minus a minus 12, that is going to be a and a. And then the two factors of 12 that are going to combine to give me 1 will be negative 4, positive 3. And negative 4, positive 3, so they get a negative in the numerator there. Over x plus 5. Now I'm going to substitute back in that x plus 2. So this becomes x plus 2 minus 4. X plus 2 plus 3 over x plus 5. X plus 2 minus 4 will be x minus 2. X plus 2 plus 3 will be x plus 5. That's what I was expecting. Okay, so now the x plus 5s will cancel. X plus 5 divided by x plus 5 is 1. And so we're left with this is x minus 2, but I have to state that x cannot equal negative 5 because, again, that was part of that removable discontinuity. I got rid of it, so I have to state the restriction that existed all the way through this problem until the very end. And that's what it's equal to. I hope that makes sense. There's a lot kind of going on here that you got to keep track of, but practice is really what's going to enable you to do this consistently correctly.